Alright, hello everyone, my name is Jordan Harrison. Today we're going to talk about heat and temperature and how those two things are related. I'm just going to take a brief moment here just to talk about the goals for our today's lesson. So we're going to first quickly review atomic structure. We're going to establish a scientific definition for temperature and explore how objects' temperatures affect each other. We'll talk about how temperature and heat are different and distinguish between the two, and we'll also hopefully get you to some calculations on changes in temperature resulting from exchanges of heat. Alright, now firstly, I want to talk about atoms. The ancient Greeks actually believed that they were indivisible, but as we know now, they are certainly not indivisible. They have different parts. We can see in the middle we have our neutrons and our protons. Neutrons are neutrally charged, protons have positive charge, and we have our electrons orbiting the nucleus. This is our standard Bohr model, which is a pretty popular model these days. And we'll be talking a lot about how these atoms are grouped together in different states of matter, as we're about to take a look at in a moment. So on your own, for a couple minutes, I'd like you to think about this question. When we're talking about solids and liquids and gases, how do the molecules group together in each of these states of matter? And also, I want you to consider, how do the forces between these molecules compare? Just make a couple quick notes to yourself, and go ahead and pause the PowerPoint, and go ahead and play when you think you've got an answer, and we'll talk about it together. Okay, hopefully you've had a chance to think about how molecules group together and how the forces between the molecules compare for these three states of matter. Let's take a look. So I'm going to start with some visuals here. We can see here for a solid that the molecules are very organized. We call this a lattice. And they don't really, and they're very strong forces between each other, and they're grouped together in a very structured way. We can see here with the liquids, it is not necessarily organized, but we do see that they're rather close together. And we know some properties of liquids as compared to solids. We know that they take the shape of their container, and that they have a definite volume. They don't really change their volume very much. We learned that last chapter in fluids. And we can see here with the gases, the molecules are much farther apart, and these little trails are indicating they seemingly appear to be much faster compared to the molecules in a solid and the molecules in a liquid. So just to quickly summarize what we talked about here. So liquids are loosely grouped with moderate intermolecular forces. But gases are freely moving with basically negligible intermolecular forces. They're moving so quickly that we would basically like to assume that they don't have much time to interact with each other. Alright, our next part here will require a little more self-reflection. I want you to take 2 to 3 minutes to write down what you think temperature is. So once again, go ahead and pause the PowerPoint for a few minutes while you consider what you think temperature is. And I want you to do it without opening any notes, without opening your textbook. I want you to know what's in your brain right now. Go ahead and take a couple minutes and do that, and go ahead and hit play when you're ready again. Okay, hopefully you've had a chance to think about what you think temperature means. Today we're going to help solidify a definition for temperature as a physicist would say it. So first I'm going to tell you what temperature is not. It is not a measure of how much heat an object or environment has. We can say that something has heat, but it is not necessarily a directly measured to temperature, but we'll talk about the relationship in due time here. So generally speaking, we can say that temperature is a measure of how hot or cold something is. Now, what does hot or cold really mean? That's not a highly scientific word that we're using here. This is the definition that I'd like you to take a moment to write down. That the physics answer for what is temperature, it is a measure of the average kinetic energy of a substance molecules. Now, for those that may not remember, kinetic energy, maybe I'll take a moment here and write this down. remember, kinetic energy, we usually call it K, equals 1/2 times m, which is the mass, times v squared. And this is important because that means that both the velocity and the mass of the particles contributes to the particle's kinetic energy. So we're talking about the average kinetic energy of all these particles. So if we assume, for example, in one gas, all the mass of the particles are the same, it essentially becomes a measure of the average speed of each of those, of all those particles put together. So one way to think about it is, the faster the molecules are moving, the higher the temperature is. Now, units of temperature, this is important. Now, we don't really use Fahrenheit in physics class. Celsius is good to use sometimes. We'll find that sometimes Celsius is okay to use if you have a difference in temperature, but in general, the safest one to use is the Kelvin. Okay? What we'll find is because the only time you should be using the number 0 is if you're at 0 Kelvin, which almost never happens. And so you don't want to accidentally enter 0 degrees Celsius or 0 degrees Fahrenheit and get an answer that makes no sense. All right, what I want us to think about next here is a few different situations, some everyday situations. We have an ice cube on a table at room temperature set for 3 hours. What do you think is going to happen to the temperature of the ice cube and table? This next one is about boiling noodles in a pot of water. The pot is hot when you touch it, but then after you turn off the stove, you pick up the pot again. Then what do you notice this time? And also putting ice cube in a glass of water, you wait a while. What happens to the temperature of the ice cube in the water? So once again, go and take a moment and think about what happens in each of these 3 situations. Pause the video and hit play when you're ready again. Okay, hopefully you had a moment to analyze these 3 situations. If the answer seems simple, it's probably because it is. I'm starting simple here. So let's talk about the first one. Ice cube on a table, room temperature for 3 hours. Well, our experiments would probably tell us the ice cube will melt, and the cube's temperature will increase. The table, you might feel, gets a little colder. After you boil noodles in a pot of hot water, the pot is very hot when you try to touch it. You wait a while, you attempt to pick up the pot again. Well, again, if it's at room temperature and the stove is off, you would probably find that the pot is cooled off, it's safe to touch. But depending on the size of the room, you might notice that the room gets a little warmer. And lastly, the ice cube in the glass of water. We've probably done this many times in our own lives. We really want a nice cold glass of water or juice or whatever it might be. We will notice the temperature of the ice cube increases and the temperature of the water itself decreases. And that's really, I guess the second part is the part we really like as humans, to drink that cold water. Now that we consider all of these different situations, what do they seem to have in common? Well, they all involve temperature being changed between 2 different objects. The question is, how does this temperature change occur? It occurs due to the exchange of heat between the 2 objects. And this is where we're going to start getting into what is the difference between heat and temperature. So believe it or not, heat is actually a unit of energy. So it's measured in joules. Heat is really a type of energy. It is defined as the energy transferred from one object to another due to a difference in temperature. As you might expect, if you had 2 objects of the same temperature, that no heat will be exchanged. So if you feel something is cold, that means that you are a higher temperature than that object. Or if you feel something is hot, then that means that you must be a lower temperature than the object, as a general rule. Although you might notice that for metals, for example, that even if it's at the same temperature, it feels cold. Why does it feel cold? Because metal is a high conductor of heat, and it can remove heat very easily from you and feel cold. You cannot remove heat from the metal so much as the metal can remove heat from you. So I want to make that distinction about when you feel something hot or cold. It likely means you're at a different temperature, but it depends on the situation. All right. Now, you're probably wondering, joules are the SI unit for energy. Why are we using calories? There is a specific reason for it. It's because a calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius or Kelvin. All right. Now, just to make the conversion here, a calorie is equal to 4.186 joules. So in certain kinds of questions, we might want to consider the using SI units whenever possible. And also, this is something interesting. 1 calorie, big C, is equal to 1,000 little c's. So in our cereal boxes, for example, or in any kind of food, they always list big calories because they don't want to tell you that you're eating millions and millions of calories. They'd rather tell you you're eating maybe only 100 big calories rather than 100,000 small calories. Kind of a marketing strategy there. All right. Now, consider this. What if you wanted to raise the temperature of a glass of water to a certain temperature, and you want to know how much heat you need to raise it to that temperature? I want you to think about what factors you need to consider in order to know how much heat you will need. Take a moment once again, pause the video, and see if you can develop some thoughts about this. And go ahead and hit play when you're ready again. All right. Hopefully you've had a chance to think about this question. Let's talk about a couple of those key factors. Now, first of all, as you might imagine, you need to consider how much water is in the glass, firstly. And you also need to think about what is the initial and final temperature of the water. So you have to think about how much you want to change the temperature, of course. And as you might imagine, the more water you have, the more time it might take for that substance to change its temperature. But there is one other thing that we maybe haven't quite talked about yet, a very special property. It's called specific heat. Now, specific heat is usually denoted by little c, and defines how difficult or easy it is to change an object's temperature. This is the equation we have for specific heat. Q equals mc delta T. Let me tell you what each of these variables represents. Q is what we use for the amount of heat required for that certain process. M is the mass of the substance that we have. C is the specific heat of the substance, and delta T is the change in temperature. I do want to note here, this can be, if you have a delta T, you can use C or Kelvin. Both are okay. The only time that you don't want to use Celsius is if T is by itself without defining a change, because you don't want to be plugging in 0 for degrees Celsius. But if it's a change, it does not matter which one you use. These are in the same linear scale. They are just adjusted by about 273 units. All right. Now, when we're using this equation, we want to think about, when we're solving a problem, how to analyze it. So you can think of it, one way is heat lost equals heat gained. This is one way. Another way is energy out of system A equals energy out of system B. So depending on your situation, you might consider a number of different ways to analyze this. All right, let's take a look at a quick example here. So let's say that we want to find the specific heat of a metal substance if 135 kilojoules of heat is needed to raise 5.1 kilograms of the metal from 18 degrees Celsius to 31.5 degrees Celsius. Again, go ahead and pause the video, and we'll take a look when you're ready. Okay, so we're going to use the equation that we just looked at. Now, C is our unknown, so we'll quickly solve this for C. If you divide M and delta T by both sides, you get C equals Q over M times delta T. So if you plug in our given values here, this is our amount of heat that's given in the problem. Notice how we did convert to joules instead of kilojoules to keep things consistent. Here's our mass in kilograms. That's an SI unit, so we're okay. And this is our difference in temperature. Again, using Celsius is okay since it is a change in temperature. And this gives us to a final answer of 1,961 joules per kilogram degree Celsius. All right, so that concludes our lesson for today. I hope you have a better idea about how heat and temperature are related and what is the difference.